Welcome everyone to part 8. And this part we'll talk about normalization, standardization, regularization, and initialization. So these are tricks that can be used to train your network, to avoid overfitting, to increase the speed of training, for example, and to increase the generalization of deep learning and neural network models. So we'll start with the standardization and normalization. So in machine learning and deep learning, if the dataset has large values, like house price, for example, or I don't know, number of population size, for example, these are large feature values. Then the system might end up with problems such as numerical overflow, because we have said before, we have a lot of multiplications within the neural network. If these multiplications are between numbers that are bigger than 1, then we might end up with explosion, gradient explosion, and numerical overflow when it comes also to the PC or the device that we are using. They have a certain numerical level, which means they, for example, for integer, how many bits, how many digits this integer number can have. We have a limit for that, and with all these multiplications, we might basically end up with numerical overflow. Also same for float, of course. If the dataset has features now with different ranges, it is even more complicated. For example, if feature 1 represents the house price, which is between 100K and 3 millions, and the second feature represents the house size, which is between a range between 30 square meter and 200 square meter. These they have different ranges. The one is from 100K to 3 million, the other is from 30 to 200. Then the cost function will be asymmetric, and we talked about symmetry, why symmetric is important. Also on the activation functions, why this is why the tan H is better than sigmoid, because also it's more symmetric than sigmoid. So symmetric basically, or asymmetric, means lower learning, and the derivative of the large values will dominate the weight updates. For example, if we are estimating the gradient along the house price and along the house size, the gradient of the house price will be always bigger, and that's what the meaning of that. It will dominate the learning process. So since most activation functions, except ReLU and its family, operates in the range close to 0, it's also better to have features that also in the same range. Actually, you're not rate same range, between the range that's small to 0 or between -5 and 5, for example. So here we have comparison between two data sets using two features here, W and B, and here W and B. Here we have normalized and normalized. Here also symmetric, asymmetric. So in this case, basically the let's say the B values and because most of activation functions except ReLU and its family, they operate in the range close to 0, it's better to have features also in the same range, which means between -5 and 5, for example, or -10 to 10. So another importance is this, as we said, symmetric and asymmetric. So let's say we have here two weights, for example, W and B. When they have the same range, let's say between -5 to 5, both, for example, or -1 to 1, then we would have symmetric cost function like this. If they have different ranges, so they have, for example, one is -1 to 1, the other is between -100 to 100, then we might end up with asymmetric cost function like this. That would cause a lot of oscillation in the training set. Here, basically, it will become much better, and here the training would take much longer, for example. Now, considering the challenge above, it's a good practice to normalize the input features to uniform range. As I said, from between 0 and 1 or minus 1 to 1. In deep learning, it's always better to have minus 1 to 1, just to know. Because, for example, for tan h works in minus 1 and 1, and the dot product, which is which is used in the similarity measures that we have talked about, works better when it comes to minus 1 to 1, or actually when it is symmetric around 0. The most common normalization method is the mean max normalization, which is given by, for example, it's x, for example, this is our value or features that we want to minimize. And here, for example, it's minus the x mean and max minus x mean. So these are the maximum value of that x feature, the minimum value of the x feature, and this is how we normalize our data set for all the features. So this is basically normalization between 0 and 1. If we want to normalize it between minus 1 and 1, we usually need here to standardization, which is basically is a part of normalization, is the transformation of the feature distribution into standard normal distribution. For example, with the mean equal to 0. Standardization, which is a part or actually a way of doing normalization, it is a transformation of the feature distribution into a standard normal distribution with a mean 0 and here sigma or standard deviation equal to 1. It's also called the z-score normalization. So as I said, it's a special type of normalization and is given by, so the normalized or the standardized here x, which is here the feature j, is equal to the feature j, for example, the original one minus the mean. So how much the divergence from the mean divided by the standard deviation of that feature. So in this way, what we do, basically, we transform the distribution of our feature xj into standard or standard normal distribution by first shifting the mean of x to 0, and then by dividing over that, basically here, the standard deviation, we make the standard deviation equal to 1. So next, basically, technique is called the patch normalization. So here, basically, standardization and normalization both can be used. Normalization is more common, but also in some deep learning papers or deep learning research, they use standardization. There is no actually rule of thumb what to use. This is the main challenge of deep learning in general, as we will see later, and as we have seen actually. For example, when it comes to which activation function to choose, there are some, let's say, recommendation to use ReLU. Here there are some recommendations to use normalization, but in general, or at the end, it's what you get after the validation, cross-validation. For example, you need to try different parameters, different configuration, different activation functions, different standardization methods until you get the best performance using the cross-validation always. So batch normalization is also used because input space is not the only feature space in deep learning. We have seen, and we have talked about that in deep neural network, for example, also which is not the shallow network, which is not only one layer network. After each layer, each hidden layer, we have always the feature maps or the new abstract features or the higher order features. This is the lowest order features, which are from the input. Then the deeper we go, the higher order feature we have. So the idea of batch normalization is not only to normalize the input space, but also we need to normalize the output of the activation functions or the activation networks. Now it's called batch because we are feeding the network with our input. We are taking that batch, which contains our basically the response to our input batch, the input data set, and then we are applying normalization on that batch. after each activation function. So it is also very recommended. It also makes the training much faster. And for example, what we see usually, it's not always used at, for example, after every hidden layer, but sometimes after every second hidden layer. Or if we talk about autoencoder, it might be used in the latent space only. Again, these are configurations that you need to test. But batch in general, for example, good practice to use batch normalization within your network, especially if you are using deep neural network, which means many layers, more than 10 layers. Regularization is very important thing to consider. It's used mainly to avoid overfitting and to increase universality and the generalization of your model. So previously we learned that the higher the capacity of the model, I'm talking about here the variance bias trade-off session. The higher the capacity of the model, the highest chance to end up with overfitting. We have more because we have actually, first of all, way more parameters than the number of training samples. We have, of course, higher capacity because we might have a higher polynomial order, or talk about neural network, we have many neurons, many layers, which means we have really high nonlinearity within the model. We also learned that the large value bigger than 1 could lead to activation explosion or gradient explosion. This also we learned. The goal of regularization is basically to add constraint on learning or optimization or on the backpropagation to avoid overfitting and increase generalization. So what the meaning of that constraint? We have basically the cost function here that we need to minimize using backpropagation. This cost function could mean square error, or could be, for example, the cross entropy. So we need to minimize that. When we said here, or when usually said that we need to consider more than one objective in our training, which means in our case here, not only we need to minimize the weight, but also we need to avoid overfitting. We need to make sure that our weights are as small as possible, because the bigger the weights are, the higher chance that we end up with a gradient explosion, and also the more chance that we have higher capacity or higher capacity, which means higher chance to end up with overfitting. So when it comes to regularization, we add other terms to the cost function. So now we have multi-objective optimization. The meaning of that, we need to minimize this term and this term as well. Here we have a weight that is usually multiplied by the constraints. And this weight, basically, the bigger the weight is, the more important this one. For example, if it is equal to 1, that means it's equally important the loss and the regularization. And that would make actually the training way slower, but also you might end up with high cost here. So remember, our main goal is to reduce the cost. The second goal is to constrain and to add regularization to avoid overfitting. So usually this should be between actually 0.01, so not that high, and shouldn't be 1, of course, because that would make the training much harder. So we have two types of regularization usually. You have L1 and L2 norms or regularization. They are also called lasso, or we have here rigid, for example, for L2. The difference is that in lasso, we need to minimize the sum of the absolute values of the weights. And here we need to minimize the sum of the basically sum of the square of the weights. So why first, if we look at that here, let's say, what is the optimum value for that? Only that, if I don't have the cost, is that all the weights are equal to 0, right? Because if all the weights are equal to 0, the value is equal to 0, then the cost would be here 0. Same for here. But since we have multi-objectives, since this is more important than this one, so this will basically let's say dominate the cost function, but we need also to look at this here. What would happen at the end? The model would try to minimize the cost, of course, would look for the weights, the optimum weights that minimize that cost, but at the same time, it would try to kind of, in this case, especially as we'll see here, to make as much as possible the number of weights or most of the weight should be equal to 0. Because here, let's say we have 5 weights. If 3 of them is equal to 0 and the rest 2 are important features, then the model would actually keep these 2 important features and the rest would be 0. And by important features, I mean then the cost would be also minimized here. And by minimizing the weight and also minimizing this one, we end up with better generalization and better performance. Now, what the meaning of these two graphs here? We see here a circle and we see here rectangle or a square. So these are two parameters, like two weights, like omega 1 or omega 2 or beta 1 here and beta 2. This is our cost function. This basically represents this part of the formula. And this also represents this part of this formula. Now, if I don't have constraint or regularization, basically the backpropagation or the optimizer would try to find this value here because this is the global minima of that cost function. Now we have multi-objectives. For example, L2 objective is to have the weights, or actually to have one of these values, because this is the geometric representation of this cost function here. And for this actually represent like the Euclidean distance, and this represents the Manhattan distance again. So this one, the geometric representation of the L1 norm or lasso is, for example, square like this. Now, if we look here, we have this the first objective and this is the second objective. What we are looking for basically the intersection between these two objectives, where we minimize the cost, but also we basically consider the better solution for this part, which should be actually along the boundary of this square. Now this is, of course, when it comes to the cost here, this is worse than this value, but for example, it's also better than other values could be here, where the cost would become higher. But also it's better in terms of generalization, because here we are also considering the let's say most of the weights would be equal to 0. Why is that? Because if you look at this square, for example, the chance that one of these ends of that square to intersect with the cost function is higher than the chance of, for example, the values that along the boundary of that square. And if we look at this end of this squares, basically this value here is equal to 1. And this is basically then the beta 1 would be equal to 1 and beta 2 equal to 0, or beta 2 equal to 1 and beta 1 equal to 1 and beta 2 equals 0, or here beta 2 equal to minus 1 and beta 1 equals 0, or beta 1 equal to minus 1 and beta 2 equal to 0. So one of these 4 angles or ends or vertices of that square, they have the higher chance to intersect with the cost function. And this is basically the game that we are playing here in the optimization. We need to minimize this one and we need to minimize this one, and what we are mainly looking at the intersection points like this one. And as I said, what is happening here at the end, most of the weights that are unimportant, for example, would be equal to 0, like here. So here beta 1 would be equal to 0, and beta 2 equal to 1. And in this case, we have a more general model. We try to avoid overfitting by doing that. If we look at the, for example, at the activation functions like relu, or not relu, like tanh or sigmoid. For example, tanh has basically two regions. One is the linear. So for the second one, which is the L2 norm, which actually not that different. Where? Because the chance of intersecting with the boundary of that circle is the same everywhere, but it's still basically it keeps the weight with a small values. So this is basically this is the unit circle here, so it's basically minus 1 1 minus 1 1. And what is happening basically here, it's keeping the weights as small as possible. It doesn't matter if one of the weights is equal to 0 and the other is not, like here, which basically what is happening because of the square. So the regularization can happen on basically the weight, but also can happen or can be used on the activations of the neurons. This is what is basically called the sparsity of the neurons, or the activation sparsity. If I have 100 neuron in layer 1, and if I add now the L1 constraint and add it to the cost function, we can see this is the output of the activations. And here's the sum of the absolute of that basically activations. What is happening here again, we are forcing some neurons to have a value equal to 0, and the rest would be basically have some value equal to 1 or high value. And by doing that, we apply sparsity. Sparsity means that if we have a vector, that the majority basically of that vector value is equal to 0. This is why it is sparse. And this is also good for generalization, because that means giving a simple or a single input, not all neurons should be on, because each neuron is looking for a specific feature, so which is different from the other features. So for example, if I have a cat image, then the neurons that are that represent the cat, for example, features like cat eyes, noise, and so on, they should fire. All the rest neurons that represent dogs or dog's eyes, for example, and so on, they should be off. And in this way, we have a sparse vector, because only some neurons that represent the cat would be on, the rest would be off. And in this way, we increase the universality, because we actually make neurons learn to only look for specific features, and these specific features would help, of course, to predict the output correctly. Now we can apply here L1, and we can apply L2 as well. As I said, L1 is harder, first of all, to train. It takes longer, but is more add more penalty on the weights, and force most of the weights or most of the activations to have values equal to zeros. This you can consider it also like model selection, automatic model selection, because we have said also in the variance bias trade-off lecture, once we train, or once we want to train a model, we start with very low capacity model, let's say one hidden layer, 5 neurons. Then if we don't, if we get high bias, which means we don't reach low performance, for example, close to 0, then we increase the number of neurons, and if we don't reach, we increase the number of layers, and so on. So we increase the capacity of the model. What is happening here, let's say we start with now thousands of neurons and 10 layers from the beginning. And now this constraint that we add here, we try automatically to turn off neurons because we have that here as a part of the optimization. And at the same time, of course, find the minimum possible cost. So we will be looking at then again at the intersection, but in this case, some neurons would be dead, which means they are not useful. We can remove them from the network, which means we started, as I said, with 1,000 neurons. If we apply regularization, we are actually at the end might be using only 100 of them, because of the constraints that we add here with the activation sparsity activation regularization. Another very common regularization method, it's called dropout. The idea of dropout is similar to L1 norm, L1 2. It's mainly similar to the activation regularization. The idea here basically that at each iteration of the backdrop, random D neurons, for example, random here as we see, this is our fully connected network. Then here at each iteration, randomly, the dropout algorithm would select random neurons from each hidden layer or also from input layer and drop them out, which means that it will basically disable them. That means they will not be considered in the forward propagation and in the back propagation. So this is basically the idea here. After each iteration, random neuron will be disabled, dropped out. A dropout, of course, has a here hyperparameter, which is the ratio of neurons that we need to drop out at every iteration. For example, 10%, or here, let's say we are dropping out 2 neurons at each iteration out of 5. So randomly means that it's not always dropping out only these 2 for layer 1. At each iteration, it randomly would select 2. For example, in the next iteration, could select these 2, and the rest would be on and do the forward propagation and the back propagation. Again, in this way, we are doing kind of automatic model selection. We are forcing the network to not first of all have redundant features or redundant neurons, to learn good features, because what is happening here at each iteration, not all features are visible or are available. It increases generalization. Let's say this is the input here, and let's say this is the color, this is the size, this is the shape, for example, and so on, features. Now, if we are hiding a part of the input feature, then the network will try to guess it, for example, and in this way the network becomes smarter. Let's say we have an image, and this image we are trying to train network to recognize cats. Now, if all the features are available, then it will maybe train easily to detect cats. But for example, we humans, if I give you an image of a cat, then if I hide, let's say, part of the face, then you would always tell me this is also a cat, even if I had a part of the part of the face. If it's a neural network with low universality or generalization and with overfitting, if it's trained on fully cat images or full cat images, then if I hide part of these cat images, then it will fail. So this is the idea of the dropout here. During the training, we are telling the network that not all information is available always. So sometimes some feature would be missing, and in this case, the neuron would try to be smarter, as I said, would try to extract more general features, more distinct features from the inputs that can be used to decide whether it's cat or dog or whatever. Now, for example, regularization is about mainly avoiding overfitting and increasing universality or generalization of the model. Also to decrease the capacity as much as possible, because we need also to decrease the computational power and power consumption of the network. Now, weight initialization is also an important trick that you need to learn, because as I said, when it comes to backpropagation at the beginning, at the very first beginning of the training, we have random weights. We initialize all the weight randomly in the space, for example, the feature space. And then we start to apply propagation and update these weights. So now how to initialize this weight? What is the optimum random function to use for that initialization? Now there are many papers about that, but now I'm just presenting to you the most common techniques. So let's have this example given a single neural model. This we already have seen. is the activation function, is the output, and this is here the linear model inside. It is clear that the larger number of n, which means the larger number of neurons here we have, or inputs we have, that means the larger number of weights we have, then we have the higher chance of explosion, because the more multiplication, the more weight values we have, the higher chance that we get of explosion. And also we have a lot of summation here between values that also make the chance of explosion higher. This is why the weight initialization is important, and also here the weight initialization should be also a function of the number of neurons or the number of terms here. So there are, of course, different initialization methods for different activation functions, because ReLU, for example, is different from tanh or sigmoid. Now, for ReLU, which is the most common one, as I said, it is recommended to generate the weight using a random number generator with a variance equal to 2 over n. So the mean is equal to 0, variance equal 2 over n. N is the number of inputs to that neuron. So, for example, if it is the first hidden layer, then these are the number of features in the input layer. If it is the second hidden layer, these are the number of neurons in the first hidden layer. So for tanh, which is, as I said, a bit different from ReLU, it's recommended to use a random generator, normal random generator with a variance equal to 2 divided by NL plus NL minus 1. So they did experiments here, and they found out basically that using such random generators, the chance to get to overfitting or to explosion is less than using other configuration, or just by using a random generator without any configuration. So that's it for session 8. We learned about 3 important tricks or configuration to consider when training a neural network. We have the normalization and standardization of inputs, or the hidden layers or the activations. We learned about the regularizations to avoid overfitting, to do automatic model selection, and we learned about initialization also to avoid overfitting, avoid explosion, and also to increase the speed of the training. Thank you.